Jupiter, a world of gargantuan storms, lethal radiation, and mesmerizing beauty, a giant whose mass is so immense it affects even the Sun itself. Jupiter has come to be one of the most examined bodies in our solar system, with 7 flybys, 2 orbiters, of which one continues to function to this day. And 2 more scheduled missions. There is just so much to learn about the 5th planet from the Sun. What makes it so uniquely red in color? What is it composed of? What lies hidden beneath its shroud-like? Clouds. What do we currently know about its great red spot, Jupiter, plays a critical role in shielding our solar system, and it's time to uncover its mysteries. Join me today as we reveal everything you might want to know about Jupiter, 5th planet. From the Sun, Jupiter is located at the edge of the asteroid belt and is positioned between Mars and Saturn's orbits. It is 798 million kilometers away from the Sun on average, or 5.2 astronomical units, and takes 12 Earth years to orbit. Once the planet's axial tilt is minimal, just 3 degrees, this implies that it does not have any significant change in seasons like Earth and Mars. And quite similar to Saturn, its equatorial radius is larger than at the poles. It is a big planet, the biggest in our solar system. It is so big, its weight is 1,000th of the weight of our Sun. That does not sound like much, but once you know that the Sun holds 86% of all the weight in the solar system, you'll find that Jupiter is nearly the rest. Its mass is sparely and half times that of all the other planets in the solar system combined, and this creates an interesting phenomenon. The barycenter between Jupiter and the Sun lies actually above the surface of the Sun at 168 solar. Ready from the Sun center, let's discuss barycenters. When we consider an object orbiting another object, we don't necessarily think that the smaller object has a gravitational pull on the larger object. That's because under most circumstances the effect is minimal, like the ISS orbiting Earth or even Mercury orbiting the Sun, but it still does occur. A barycenter is the center of mass between these two things in orbit, or where in space they both orbit. About with Jupiter being mass and Sun distance it is. Unlike Mercury, its impact is anything but small because Jupiter orbits around the Sun. Both of them do a bit of a dance around this center of mass, which is really above the surface of the Sun. Let me illustrate this principle with an example. Suppose I take a heavy object and a lighter object and place them at the 2 ends of a long rod. So that the rod would balance, we must locate the center of mass. As you can see, the center of mass is near the heavier object. Suppose this is the Sun and Jupiter, with thestic being gravity, and you'll know how a barycenter works. While Jupiter has the largest mass of any planet in our solar system, it is not the densest. It is the most massive because it is the largest. If Neptune was the same mass as Jupiter, it would be the most massive. And if Jupiter were the same mass as Earth would be more than 4 times larger, as it is. Although the diameter of Jupiter is 11 times the size of Earth and its overall mass is 318 times greater than Earth's, as we are aware. Mass influences gravity. This means that Jupiter possesses a massive gravity over 2 times that of Earth at 2528 g on its surface. The gravity of Jupiter has such an impact on the solar system that it touches every planet to some degree. Its gravity is sufficiently powerful to rip apart asteroids and pick up 67 moons. At least, some researchers believe that Jupiter annihilated numerous celestial entities in the distant past, as well as avoiding others. Planets from existing. One such instance of this specifically is for Vesta scientists. Even forecast the gravity of Jupiter is that strong around the solar system that it is already affecting Mercury's highly eccentric orbit, so much that in a few billion years the small planets may either collide with the Sun or get thrown out of the solar system altogether at the time, although it may be the savior of the 4 inner planets. Without Jupiter being a cosmic vacuum cleaner, it wouldn't be pulling in hazardous objects such as long-period comets or disrupting their orbits, so much as to kick them a bit of energy so they exit the solar system altogether. Jupiter is the 5th planet from the Sun, and it's 5 times farther away from the Sun than Earth. Even so, it can be the 3rd brightest thing in the night sky following the Moon. And Venus descends. To just want to demonstrate how bright it is using just a handycam. We can see Jupiter fairly easily in the night sky with a peak magnitude of 294. It can actually make shadows because of it being so obvious in the sky. It makes a very nice target for amateur astronomers. as consumer telescopes have improved in recent years. It's amazing what details you can see from your back garden, and what makes these famous patterns. The cloud layer is only about 50 kilometers thick and contains ammonia crystals, much like on Saturn. But the coloration comes from compounds heating up from deep within Jupiter. And then rising these substances are referred to as chromophore, and when they arrive at the clouds, they react with the UV light of the sun to produce these incredible multicolored bands. This is pretty much a cycle, though, and the face of Jupiter may change quite a lot over time. Even if their colors do change, the actual latitude of these bands is nonetheless stable enough to be assigned identifying designations, but they can change in width over time. Many storms and turbulence are present where these bands intersect, and it is the reason and engine of Jupiter's much-renowned Great Red Spot. This storm is colossal. It could easily accommodate the diameter of Earth inside it. That's been around as long as we've known, since its discovery in the 17th century. It could very well be a permanent feature of the planet, but curiously it has gotten smaller in size. Since it has been observed, the cause of its reddish color is yet unknown, and the spot can have very different colors, ranging from brick red to almost white. The latest theory for its color is chemical compounds being dispersed by the UV light from the sun, much in the same manner as the mechanism which occurs on the rest of the planet. The storm is actually much higher up in the atmosphere than the surrounding clouds, and, as a result, can interact with the sunlight a lot more. This would explain why its color can be much stronger than anything else around it. But Jupiter doesn't just have one scientifically interesting storm. Another storm, known as Red Spot Juno, formed when three storms merged into one between the years of 1998 and 2000, and it has so far gone unscathed by its larger neighbor and is now quite a notable landmark of the planet. It might continue for another few hundred years if it escapes the same destiny of a comparable storm that went straight through the middle of the Great Red Spot. So what do we believe Jupiter is composed of? Well, somewhat similar to Saturn beneath the atmosphere are liquid, and then they're metallic forms of hydrogen. The further you go on the planet, the more pressure there is under tremendous pressure. Hydrogen behaves as a metal. And then there is an ice or rocky core, because we cannot replicate on Earth the tremendous pressures Jupiter has, so we do not actually know what properties these substances possess. At the core, approximately 90% of Jupiter is believed to be hydrogen, 10% helium, and then trace quantities of methane, ammonia, and others. Jupiter spins very quickly, faster than any other planet, taking a rotation in just 10 hours. But because it's not solid, it does not spin the same speed throughout a rotation, at the poles taking 5 minutes longer than at the equator. As a kid, I wondered greatly why Jupiter wasn't a star, given Jupiter is so huge, and also it's comprised mostly of combustible hydrogen. Gosh, surely someone just has to toss a match in to ignite it. Well, the sad news for my inner child is that stars don't exactly function like that, and also there's hardly any oxygen on Jupiter for a combustion to take place. Stars generate their heat from nuclear fusion due to the intense pressures present at the star's core. Current theory is that Jupiter would have to be approximately 75 times heavier than it currently is to be large enough to class as a star. Although interestingly, its volume isn't far off from the smallest known red dwarf. And yes, you might have noticed in this photo, Jupiter actually has rings nothing on the scale of Saturn, but there are 4 planetary rings. The main ring is highly thin but extremely bright, the others quite broad, but extremely faint. The main ring is 6,000 kilometers wide, and the only prominent feature you will find is what is called the Met, this notch. Something else to look at about Jupiter is its extremely strong magnetosphere. It is 14 times stronger than Earth because the planet's liquid metallic hydrogen center. This makes it the most powerful magnetosphere of any planet in the solar system, and is only surpassed by the sun's sunspots. There are a few reasons that this is truly fascinating. The first is that magnetospheres direct solar wind into the planet's pole, which creates beautiful aurora. The second is that the 4 largest moons of Jupiter are shielded from this solar wind due to the fact that they exist within the magnetosphere. This means they don't require individual strong magnetospheres because Jupiter is taking care of it for them, but that doesn't mean that they're immune to radiation. Jupiter itself has a strong radiation band around it, the same radiation band that has ruined any probe that flew through it. The nearest big moon to Jupiter Io cuts directly through the center of this radiation belt, getting 3,600 RAM per day on the surface for a point of reference. Anyone exposed to this amount of radiation would be dead in 4 hours. Not the best house away from home. Then, when I mention the Jovian moons, I'll only very briefly discuss them because I've made a separate video set on them here. Jupiter has 60-some known natural satellites, 51 of them less than 10-kilometer diameter. But the Galilean largest moons are among the largest in the solar system. They are Io, Europa, Ganem, and Callisto. And they're all interesting in their own right. Ganem is actually the largest moon in our solar system and has a larger diameter than Mercury. And with that final comment, look at Jupiter in infrared, showing the sheer size and strength of this planet. This dot at the bottom of the planet is the collision of an object from space which, if it had HD Earth, might have meant the end of our world as we know it. We are thankful that Jupiter is there, not only because of its good looks, but because in so many respects it is a treasure to our solar system. I think most of us are familiar with what the planets look like in the visible light spectrum: Saturn's pale golden color, Jupiter's red bands and colorful clouds, and Neptune's dark blue hue. However, light is emitted or reflected by planets in wavelengths outside of our eyes' capabilities, like infrareds and ultraviolets, and usually what is visible in these wavelengths is really more precious to scientists than just the way a planet would look to the natural eye. That's because some things which are not visible to our eyes could be quite visible in infrared or ultraviolet or vice versa. And if we wish to learn about what substances are present on a planet, the electromagnetic spectrum can assist us. Once more, first of all, let's examine how Jupiter looks in natural light. The many spacecrafts that have flown by Jupiter have shown it to be a lovely planet. You will immediately notice a lot of the primary cloud deck of Jupiter in visible light. These are not water clouds like the Earth's, but more ammonia ice clouds. If you look closely, you can begin to notice the various altitudes of these clouds. The dark, thin areas are really shadows cast by the tall, lighter color clouds. It looks like the higher in altitude. These clouds are the lighter they get, which can be noticed in the highest altitude pop-up clouds in this area, which are white, snowy white. The process involved in the various colors in Jupiter's atmosphere isn't fully understood, but it's thought to be triggered by the upwelling of substances which were formed deep within Jupiter, suddenly being exposed to the UV light from the sun. As they rise up to the top altitudes in the atmosphere of Jupiter, these substances start to darken, eventually falling back down again to the lower altitudes. But as you can see, Jupiter's ammonia cloud deck is opaque. We can't see through it if visible light was the only wavelength of light we had to work with. The vast majority of Jupiter would be a complete mystery. Fortunately, we also have instruments that are able to see more than our eyes are capable of, and in some wavelengths of the infrared, we are able to view Jupiter in an entirely different light. Perhaps the most dramatic is to look at Jupiter through the use of the 468-micron wavelength, as this displays the heat of the planet. Very interestingly, in this view taken by the GER Observatory, it is the lower altitude reddish bands that are the brightest. You see, Jupiter actually emits more heat than it receives from the sun. It is contracting in size, which heats it up. This heat eventually makes its way out of the planet through the cloud deck. The heat escapes easiest where the cloud deck is thickest, which is why structures such as the Great Red Spot and the white bands, invisible, light or dark in this picture. Fortunately, we aren't stuck with a this view of Jupiter either. Due to the Juno spacecraft currently orbiting Jupiter, looking at Jupiter's poles in infrared, once more scientists were able to create a 3D map of the incredible vortices that are found there. Jupiter's North Pole has 9 seemingly constant vortices, 8 in a square shape revolving around a large, one found right in the center. Again, you'll notice that it is the lowest altitude regions that are emitting the most heat, because this wavelength only reveals heat. The haze and shadows in the atmosphere don't block the view as much as you would get in visible light, meaning it can provide us with an unprecedented view of the 3D structure. Of these vortices, it's still quite cool here by Earth standard. Even the yellow parts are only 3 degrees C, with the darker, higher altitude areas being 83 degrees C. And because the heat is emanating from Jupiter itself, this view is accessible to Juno. Day or night it is in sunlight. Dependent storms can appear in infrared before they're detected in visible light as well. Observe this comparison captured by Hubble. These near-Earth's sea-ice storms found below the cloud tops are much hotter than the ambient environment, meaning that internal heat does have significant part to play in creating atmospheric perturbations. And while we're at wavelength, let's take a brief glance at Jupiter's volcano moon, Io. Unsurprisingly, Io's night side is completely illuminated by the volcanic eruption on its surface, which makes it very easy to detect new volcanoes and Tamaniter. The ones we previously knew about Juno has had a few glances at Io, each one unveiling it to be a hub of activity, a real hellish but fascinating world. In fact, all of the Galilean moons have been studied in infrared, but using specific wavelengths, which can show different things. For example, here is the infrared view of the Galileo probe's Europa in the 1.5 micron water band. When looking at an object through this specific wavelength, we can see areas where water is present. The deep blues in the image are the areas of the purest ice water, while other colors represent a combination of ice water with different minerals. This is referred to as spectroscopy, where you can determine what molecules are on a planet without even needing to land there. You notice when white light bounces off of a certain molecule or atom, that molecule will take in a band of light and bounce back. The rest, if we examine the missing band of light, we can understand what the molecule is. So consider this image more as a graph than a photo of positions of some molecules' colors arbitrarily selected by a scientist to denote the data. For example, if we examine this photo of the absorption band for sulfuric acid, it's the light areas this time that indicate where the concentration of sulfuric acid on Europa is. This concentration is located near the cracks in the surface. So perhaps it originates from the ocean beneath the crust, but it also occurs in the trailing side of Europa. Displayed at the top left of the image, it appears that as Europa goes around, it is pummeled with sulfur ions. Amazingly, this sulfur likely came from the eruptions of Io volcanoes. If you take a look at a crater on Callisto, infrared data has been placed on top of a visible light image. Reds show more water ice, blues show less. This is sort of interesting because this is one of the best resolution infrared images we have of a body around Jupiter. This image only being 200 kilometers across, it adds a lot of information you wouldn't get from the visible light image. Namely, there's a concentration of water in the crater, but a ring directly around it where no water is present, and then water appears again in this ray system coming away from the crater. The icy areas originate from the impactor stripping away the ice under the surface. But whereas there's a ring between the center crater and the debris of the ray system is somewhat of an enigma. Perhaps the icy debris of the impact did not begin falling to the ground until at this distance. Out in any case, this image indicates that non-ice material only make up a thin layer on the top of the surface of Callisto. And what does Jupiter look like through certain bands of infrared? This image is really interesting, the top left and right. The images are taken in 1.61 and 2.73 microns respectively in these bands. We can see the cloud deck similarly to what we can see in visible light. However, in the middle, we are looking only through 2.78 microns. The absorption band of hydrogen, as we know, Jupiter is predominantly hydrogen, meaning the hydrogen in the atmosphere suddenly becomes opaque and visible in this wavelength. In fact, the only features still visible are the really high altitude clouds, the ones that poke through most of the hydrogen in the atmosphere. The bottom left image is the 3.1 micron band, where there is some absorption, but less so. At this band, it's methane and ammonia. That air absorbing the light bottom middle is at 4.99 microns, providing us with another heat map, and bottom right is a false color composite of all 5 images, which is what you can see occurring. If ever I show a false color picture in one of my videos, now you know what these false color pictures are attempting. To display the last fascinating perspective of Jupiter I would like to display is in the ultraviolet absorption spectroscopy. The ultraviolet is not very helpful in planetary astronomy. The only instance I can think of it being used on Jupiter was to monitor the effects of Comet Shoemaker in 1994. There the dust absorbed plenty of the sun's UV light, and therefore scientists could easily monitor winds in the planet's stratosphere by observing the progression of these structures. But molecules that are hot enough will also radiate light in plenty of various wavelengths. And there is a brilliant source of light emitting from Jupiter in ultraviolet and infrared, its auroras. Jupiter's auroras are really strong relative to Earth's ones and are a permanent fixture on the planet Hubble, which can observe in ultraviolet, has been monitoring Jupiter's auroras for years. Albeit the best observations have come from Juno in the infrared, simply because Juno's orbit places it above the planet's poles, while Hubble's observing angle makes it hard to observe. These auroras are heavily influenced by Jupiter's magnetic field. Environment streaming particles into its upper atmosphere, along with from the flux tubes between it and its moons. So there we have it, a glimpse of Jupiter in a much different perspective than what you might be accustomed to. And as you see, absorptions and fluorescence by spectroscopy can lead us to know a planet much more than what only visible light provides. We can ascertain molecules and minerals, watch a planet's heat map, and see aurora, interacting with the planet's magnetosphere, everything together. Helps us get a more complete picture of how a planet works and why it behaves the way it does. What more videos about this for the other planets? Let me know in the comments below. In July of 1994, scientists around the world watched in amazement as the comet Shoemaker-Levy 9 smashed into Jupiter. The impact's blast was so dramatic that it released a force equal to 300 million atom bombs. For 6 days, Jupiter was throttled by 21 discrete impacts from the comet's fragments, which created giant glooms of debris that rose 3.00 kilometers above the cloud tops, an impressive display given Jupiter's overwhelming gravity, and warmed Jupiter's atmosphere to temperatures of up to 30,000 degrees C. At the moment of collision, the comet was flying at a scorching 216,000 km pH, with its largest piece measuring 2 kilometers in diameter. The collision produced enormous clouds of wreckage that were seen for months, and created a scar in Jupiter's atmosphere, seer more visible than its great red spot. Now collisions of this type aren't quite unknown too. Our solar system is full of records of huge impacts caused by comets and asteroids. Scientists suspect the Earth was struck by a huge asteroid at the close of the Cretaceous period, which would have caused the extinction of the non-avian dinosaurs. But these occurrences are incredibly few in number, so the opportunity to observe one happening is a once-in-a-lifetime opportunity. So, what did it look like? And does the incident enlighten us on the chances of an event such as this occurring here on Earth? Join me today as we revisit the largest planetary explosion ever viewed from space and dissect what it taught us about Jupiter and planetary collisions in 1993. Astronomers Carolyn and Eugene Shoemaker and David Levy were doing research at California's Palomar Observatory when they found a periodic comet that had been caught by Jupiter's gravity. Periodic means the comet has an orbital period of less than 200 years. This was rare because most comets in the solar system have orbits around the Sun. However, Jupiter is so large, being the biggest of the 8 planets by a long shot, that its capacity to capture other objects coming to its orbit isn't an unexpected thing. A lot of Jupiter's irregular moons are probably captured asteroids and comets that have since outgassed their volatile material on their surfaces. But this comet also possessed other strange features. For one, it was huge, so huge that scientists believe that the frequency of such impacts is a 1 in 6, 0-year event, but the comet was also shattered, probably pulled apart by Jupiter's tidal forces on an earlier approach. Most striking of all, however, was his extremely eccentric orbit. Eccentricity measures the deviation of an orbit from a circle, with 0 being the value of a perfect circle and 1 being the maximum time an elliptical path becomes hyperbolic. Shoemaker 99's path had greater than 0.998 eccentricity. That is very eccentric. Practically, as soon as astronomers noticed there was a chance the comet was going to crash into Jupiter, but their doubt became sure once they gathered more accurate data. Soon enough, astronomers knew the collision would take place around sometime during July 1994, and soon the entire world was on the edge of their seats, waiting for the event with bated breath. Expecting SL9's effects, astronomers tracked its path from the observatory, Germany's Rosat X-ray telescope and NASA's Hubble Space Telescope, among others, but when the first of the comet's fragments struck on the 16th of July, 1994, the worst possible scenario took place. It seemed like we would miss the spectacle. You observe SL9 trajectory meant the impact would take place on Jupiter's far side from us. That meant none of Earth's powerful telescopes were in position to observe the first impact for scientists. This would have been a devastating disappointment. But, luckily enough, not all our cameras were pointed here on Earth. By sheer chance, NASA's Galileo spacecraft, launched in 1989, was but a year behind Jupiter. When SL9 made its final approach, it just so happened to be in the ideal position to capture the impact as it occurred, but Galileo wasn't our sole assistant. From afar, the spacecraft, which had been launched in 1990 to observe the Sun, was also aimed at Jupiter, and even NASA's Voyager 2, 4 astronomical units away, was programmed to scan the radio emissions from the crash site. With his ultraviolet spectrometer, every pro suspended its own missions to collaborate on this to enable us to see a remarkable event shortly after fragment. A hit Jupiter, Galileo observed a huge fireball explode, reaching up to 24,006 plume, rose sharply, 3,000 kilometers, which would have it as large as Australia from north to south. This was unexpected. Scientists hadn't anticipated the appearance of fireballs in the wake of the collision. A few minutes afterward, masses of thrown out debris hurtled back toward Jupiter's surface and disintegrated again, making Jupiter's atmosphere a blazing furnace. Shortly thereafter, Jupiter's rotation carried the impact zone, and with that, Jupiter reminded us once again of its colossal power, both as a protector of our world and as a stage for some of the most dramatic events the solar system has ever revealed. But what happens when that very power is tested? When a comet shatters and slams into Jupiter with the force of millions of atomic bombs? That's exactly what the world witnessed in 1994. This is just the beginning of Jupiter's story. The rest awaits in Part 2. Thanks for watching.